In this final video, we're going to talk about some formal notation for finding areas under curves by estimating with rectangles. So let's say I have this curvy function f of x, and I have a left endpoint given by a and a right endpoint by b, and I want to approximate the area under this curve. And I'm going to do so by breaking it up into a bunch of rectangles, all with equal sized bases, and then for generic sake, let's say that I break it up into a total of n rectangles. And just for the sake of argument, let's go ahead and do it as a left endpoint sum. So I'm going to say that as L sub n. L sub n is going to give me the area under this curve where I have n rectangles, and I'm taking left endpoints for the heights of each of these rectangles. And you see that as the curve shifts, sometimes those are going to be over approximations and sometimes they're going to be under approximations for the area of the curve. And in order to find out what this sum is equal to, I first have to find out, well, what is the width for one of these generic rectangles? And I'm going to call this width delta x, which is also a change in x value. And what is this change in x? We can be really precise about what delta x is equal to because we know the width. The width in this case is the length from a to b. And how do I know what that distance is? It's going to be the difference of b minus a. Just as before, when we had endpoints of 1 and 3, the total distance here was 3 minus 1. It was 2 units total. And we broke it up into 4 rectangles, so 2 divided by 4 gave us our width of 1/2. Here we have a total distance of b minus a, and we're breaking it up into n pieces. So my length of the base of the rectangle is going to be given by b minus a over n. So this is my length. I shouldn't call it length, I should call it width. Anyway. And what is the height of each of these rectangles? There are a number of ways that we could write that. In this notation we have a, and then this next place is going to be a plus delta x, right, because we moved a delta x unit over. And then the next x coordinate is going to be a plus 2 delta x, and then the next one is a plus 3 delta x, and so on. A faster notation for this, and the notation that I'm going to use, is going to be the first area, I guess, is going to be given by, the height is going to be f of x1. Because I'm just going to say that this first rectangle, it's my first rectangle and I'm taking the x coordinate in the first rectangle, that's x1. And I want to know what is the height at x1. And so for the first one, x1 is actually equal to a. And then the width of this rectangle is given by delta x. And that gives me the area of my first rectangle. What about the area of my second rectangle? It's going to be the height of some point in here, which I'm going to call x2 because it's living within my second rectangle, times the width of that rectangle, plus f of x3 times delta x plus dot 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 plus f of x. How many rectangles do we have? N rectangles times delta x. Sort of ran out of paper, but you get the idea. So this is a long way to write out a generic summation of all of these rectangles. I'm going to do one more thing, and that is to formalize this. Instead of writing out this with all of these steps, there's another way that we could do it, and we could do it by using a sigma notation. The sigma notation, this is a capital sigma, which is a Greek letter, if you don't know that, and it stands for sum. That's why we use a capital sigma for sum. And what am I summing up? I'm summing up a whole bunch of different pieces, and the pieces look all really similar, right? The only difference is the subscript on the x, because we're changing what our input is that gives us the height of each of these rectangles. So all of these look a lot like x sub I delta x. And the sum notation, I'm going to keep track of how many times I'm doing this. I want to start when I equals 1 and keep summing up until I is equal to n. And that's what this subscript, this is my starting place for I. And this is where I end. I'm not going to hold you responsible for being able to generate this notation in this course. However, I think that it is important that you're exposed to it. So if I write something like this down, you're able to interpret what's going on. This is saying that I start when my I value is 1, so my x of I, and I'm going to keep adding this over and over and over until I get to an I value of n. So this is the way that I would write the sum of my left endpoints of these rectangles. And the final thing that I want to get to, and this is the thing that we were hinting at when we looked at that technology, is that if I took the limit of all of these sums, so if I look at the limit as n approaches infinity of this sum, now the notation looks crazy, but really it's a pretty easy thought that we're talking about. Of my little rectangles, this is going to be exactly equal to the area. And this is where calculus is a little bit magic. How can I say that it's exactly equal to the area when all we were doing was doing a bunch of approximations? And that's the beauty of limits, that this no longer is approximation when I take the limit to infinity. What is actually being taken, the limit in this case, is this number. This sum gives me out the area of a set of rectangles. And as I get more and more of these rectangles, the areas get to be a better and better approximation, and that better and better approximation gives me a set of values that approach the area value. So this is messy notation for something that's a really easy idea, that we're going to use a bunch of rectangles, and as we get more and more rectangles, the areas of those rectangles gets closer and closer to the actual area of the curve. And this is the fundamental building blocks for how we're going to approximate areas, or how we're going to calculate areas moving forward in the course.